And welcome to Sanford Flip Math. We are working on AP Calculus. We are about to wrap up the chapter that is about applications of derivative. This is chapter 4 in the Finney, Demana, Waits, Kennedy book. And this section is about related rates. Related rates are rates that shockingly enough, relate to each other. In other words, it's when we have more than one quantity changing with respect to time. So we might be talking about velocity of one thing compared to the velocity of another, or maybe components of velocity. Maybe we're talking about how one side of a triangle is changing and how that affects the other side and things like that. There's a basic process that needs to happen, and that is we need to write an equation including all the quantities that are in play. So, and we'll see some examples of that. Then we're going to take the derivative with respect to time, and this is going to feel weird initially. You might have x in the middle of the equation somewhere, but really what you're going to be taking the derivative of is with respect to time. So everything's going to be d something dt. So we might have dy dt, we might have dx dt, we might have d something else dt, and all of that's going to be in the middle of the same equation that maybe t didn't appear in at all. Okay, so that's going to feel different. Okay, and then at the end we're going to substitute and solve for whatever quantity that we're looking for, whatever answers the question. So let's just see some examples, and we'll go through this. Okay. All right. Here we go. Okay. So what we have is a ladder leaning up against a house. It turns out the ladder that we're working with is 20 feet long, and it's a dangerous situation. The ladder is actually sliding down the house. It's the top of the ladder is still leaning on the house, but it's sliding down the house, and in the process the bottom is sliding out. Well, that's kind of obviously not a good situation to be on the ladder, but what we're saying is that as it's sliding down the side of the house, it's doing that at a rate of 0.5 feet per minute while the bottom's sliding away. Now our question is, how fast is the base of this ladder or the bottom of this ladder moving away? Okay, so I'm going to kind of streamline my little picture here. Okay, so here's the vertical part of the house. Here's the ladder, and here's the ground. Okay, so house, and then ladder. And probably worth noting that we're going to make an assumption that the house is perpendicular to the ground. And I know that's not always the case, but we always have to assume something, and by golly, that's what we're going to assume. Now, the ladder is 20 feet long. Now, the ladder is 20 feet long the entire time. So as the ladder is sliding down the house, and again, the bottom is sliding out, while that's happening, the ladder still stays the same length, okay, that 20 feet long. Okay, that's 20, that's not 2, and then off. Okay. Okay, so what we need is an equation that relates all of these things. Okay, so write an equation that relates the ladder's length, the height up the house, and how far away it is on the bottom. And the key is really this issue of that right angle. So this makes this a right triangle. So that means I can use, you guessed it, the Pythagorean theorem. Okay, so a squared plus b squared equals c squared. Now, I'm going to use letters that make sense in terms of direction. So like I'm going to call this side x, I'm going to call this side y, and we can call this whatever you want, but the fact is this 20 is not changing. That 20, okay, so the only time I can substitute a number in right out of the chute, right at the beginning, is if that value is not changing. So the Pythagorean theorem says a squared plus b squared equals c squared. And again, I'm not using a's and b's and c's, I'm using x's and y's. Okay, and so I'm just going to write this one more time because I don't really want 20 squared there. Okay, now the next step in this process says take the derivative with respect to time. Okay, so what I have to do is I'm going to do d something dt all the way through this problem. Okay. Now, we've seen this kind of thing before, but it's been like doing the derivative with respect to x, and if we're doing if we end up doing the derivative of y, we throw a dy dt in. It's kind of the same idea. Okay, so the derivative of x squared is going to be 2x, but I'm really not doing the derivative of x squared with respect to x. I'm supposed to be doing it. So I'm doing the derivative of x squared. I did it with respect to x, and now I need to multiply by dx dt. So really it's a little chain rule thing going on there. Okay, and I'm going to keep that going. So I'm going to do the derivative of y squared with respect to t. So this is 2y dy dt. And then I'm going to do the derivative of 400, which you guessed it, is 0. Okay. Now, this question is asking, how fast is the base of the ladder moving away from the house? Okay, so the question is, how fast is the base of the ladder moving away? So they want to know how the velocity here. Well, that's the rate of change of x. I want to know dx dt. That's what this question is actually asking me for. Okay, so that's, I want to just make a big stink out of that. There it is. Okay, and again, I know how fast is the base of the ladder, so at the bottom, moving away from the house. Okay, so again, that's in the x direction. Okay, now one other thing to note here is it's sliding down the house, slipping down the house at a rate of 0.5 feet per minute. So the question is, what's that? Well, that's the rate of change vertically. So that is actually, dy dx. Or I'm sorry, dy dt. Rate of change of y with respect to time. Okay, so quick little note. We are told dy dt is 0.5 feet per minute. Now, one little adjustment here. Since this is moving down the house, the y value is getting smaller and smaller, so this is really negative. Okay, so you need to be aware of the fact that since y is getting smaller, it's decreasing, that rate of change is really negative, and that should be something that you pick up in the process of solving, and that's not obvious. Okay? All right, so what we're going to do is try and solve this thing for, again, dx dt. This is what we want to solve for, and I should have done the picture, or I'm sorry, the highlighting in the same color that I did on the right. Excuse me. All right, now it says we're supposed to do this when the ladder is 15 feet from the ground. Well, I'm going to go ahead and solve this for dx dt because I have to do this a couple of times. So you don't necessarily have to solve for dx dt right now. Anytime, once you have done the derivative, then you can substitute at any point there. The only catch is that I know that I'm going to do this twice because I asked you for two different situations here. Okay. All right. So I'm going to go ahead and solve for dx dt right now. Okay. So 2x dx dt. Again, I want to keep that. I'm going to subtract this whole term from the other side, from both sides. Okay. And then I'm going to divide both sides by 2x. Okay, so ultimately what I have here is dx dt equals, now the 2's will divide out, so y over x times dy dt. Okay, now this is going to get me anything I want. Okay, so quick little note. What 15 and 10. Okay, so when y is 15 feet, and then I also want to find out when y is 10 feet from the ground. Okay, and dy dx is negative 0.5. Okay, so dx dt equals 15 over, Okay, so this comes in here. The 15 goes in here. Now here's the other little problem. What's x? I don't get an x value. They don't tell me an x value. But I need you to remember that this all came from, where'd it go? Oh, there it is. It all came from, let me highlight this. And this is where I'm going to get my x values. Okay? Okay, or if you like the other version of it better, x squared plus y squared equals 400. Okay, so a little note to self here. Okay, so I need to go back and find x. $225, so 175. So x is the square root of 175, which is 5 root 7. Okay, so I'm going to go ahead and just type this into the calculator. We could play around with it and get an exact value, but I don't really care. So we get negative, yes, 0.56694. So if we go to 3 decimal places, which is what AP generally likes, 5, 6, 7. Now you can keep more on the AP exam, that's fine. Okay, one other quick little note here. This was in feet per minute, and this is also a velocity. So I'm going to do this in, you guessed it, feet per minute. Okay, so units are a big deal. I don't know what just happened there. Okay, come on. I'm making a mess. Oh, there it went away. Okay. Okay, so that's one of them. That's the one answer when the height is 15. Okay, and really it's not a big deal now to substitute in one more time. That is funny. There we go. Okay, not quite that far. Okay, so dx dt again. Okay, so when y is 10 this time, over and negative 0.5. Now again, I don't know the x value for this, so I have to do 10 x squared plus 10 squared equals 400. So x squared equals 300. X equals 10 root 3. Okay, so 10 root 3. Okay, so I'm going to approximate this, and that is negative 0.2886, whatever. So negative 0.289, and again, that's feet per minute. I see what happened. I touched the, come on. Whatever, that's fine. Okay. Alrighty then, so that's an example, a full-blown example. We've done a couple of things there. Okay, I'm going to do one more, and I had planned on 3, but the third one's a long one, and we haven't even gotten through the second one yet. So, all right, what we're saying is, it's funny how it wrapped. Sorry about that. This is supposed to be one equation, and it's supposed to look like that. Okay, particle is moving along a graph of y equals x times 4 minus x. Okay, and if you prefer, that's 4x minus x squared, or if you'd prefer negative x squared plus 4x, that's fine, it doesn't matter. Okay, so I have this graph, and it has zeros at 0 and 4, and it's going to do something like this. Okay, and the idea is that, what I'm going to do is I'm going to put a point here. I have some point that's riding on this graph. So the idea is that it's cruising along here, riding on this graph. Some kind of a particle, and what it does is it moves on this path. So imagine this like a little train track, and I have a tiny little train on that track. Okay. Now what it says is, particle moving along the graph of y equals blah blah blah, and it's moving at a rate of -1 centimeters per second. Now we're saying that this graph is numbered in centimeters. -1 centimeters per second. So it's moving to the left. How do I know it's to the left? Think about that. And it's going 1 centimeter for every second. Okay, so that's the direction it's going, like that. Okay, so now the question is, what is its vertical rate of change? Okay, vertical rate of change. Now I'm going to use something clever for that, dy dt. That's what we want to know. Okay, that's our goal, is to find out dy dt. And I'm going to use kind of an obvious labeling here that there's x direction is going to be horizontal. So probably worth noting that the horizontal rate of change, so dx dt is -1 centimeters per second. Okay, sorry, I started right meters per second. Okay, so I need to kind of keep that in mind. Okay, all right, and then it says we're going to find the vertical rate of change at those two different x values. Okay, all right, so what we're going to do is write an equation that puts all this together. Okay, so I need an equation that has both the x value and the y value in it, because those are the only values I'm talking about. Well, turns out that I have one of those. It's just y equals -x squared plus 4x, or whichever form you like. That has both x and y in it. Okay, so what I'm going to do now that I have an equation, is I'm going to take the derivative with respect to time. Okay, so the derivative of y with respect to time is dy dt. The derivative of -x squared would be -2x, but it's with respect to time, plus the derivative of 4x would be 4, again, with respect to time. Okay. All right, so at this point, I just want to solve this thing for dy dt. It's magical, and that's a hard problem. Okay, and then but in order to do that, I need an x value and a dx dt. Well, it turns out I have a dx dt, and I have an x value. Okay, so we're just going to do a little, the little theme song for Glade or whatever. Plug it in, substitute. Okay, so -2 times, okay, we'll do this for the x equals 3 first, times, and we said dx dt was -1, plus 4 times dx dt, so -1. Okay, so this is now 6 plus a -4, so 2, and we said this whole thing was done in centimeters per second. Okay, and what's interesting to me is this is positive. Okay, so what does that mean? This really means that y is actually in the process of going up. Okay, now let's go back to the graph. It said when x is 3, now remember this thing's moving to the left, but I'm stuck, so it's moving this way at -1 centimeters per second to the left, but it also is saying that I have to stay on this track. So as I'm going to the left, when I get to x equals 3, I'm actually going, so I'm going to the left at -1, but I'm also going up at, what was it, 4? 2. Yeah, up at 2. Okay? So that's the context of the situation. That's what's going on. Okay? All right, one more little chunk here. It also asks us to find out when x is 2. Okay, so when x is 2, I'm going to do the same thing I just did. Okay, so dy dx equals -2 times x times dx dt plus 4 times dx dt. So this becomes -2 times +2 times -1 is 4, plus -4, or 4 minus 4, so 0. So what's that mean? That means it's not going up. And it's not going down. So again, let's go back to the context of the situation. We'll just leave it alone. All right. So if I move this point to here, now remember we're going along the track here, and when I get to x equals 2, and as I'm going to the left right now, okay, so I'm still going to the left, at 1 centimeter per second to the left. This thing is actually headed straight horizontal at this point. So that's not up, that's not down, it's just horizontal. Okay, so that's what that means. Okay. All right, so those were two fairly straightforward problems, and let me just say that these are very, very common types of problems to be working with here. Okay, well, we're going to leave it at that, and we will do more in class, but this is our first little dose of related rates. We'll be on this section for probably about 2 more days anyway. So, all right, thanks for watching. Talk to you later. Bye.